Problem statement. The flow rate is measured to be 0.12 cubic feet per second from the pipe shown in this figure. Find the loss coefficient of the valve. Neglect wall friction. The question is to find the loss coefficient in this valve. So it's asking us what is the K of the valve. Also, we know that the loss coefficient at the entrance for a well-rounded pipe from the textbook, we know that this value is 0.03. Okay. Also, it's asking us that we should neglect wall friction, which means that the friction losses, which are friction losses, which are FL d velocity squared divided by 2g, that is equal to 0. Okay, so to be able to get K valve, we have to apply the equation of energy between 2 points, and we can choose, as we mentioned before, point 1 uh, at the reservoir surface and point 2 at the outlet where the pressure is atmospheric. So the pressure here is atmospheric, and the pressure in one is also atmospheric. So if we apply the energy equation between 1 and 2, we would have the following. So we have a energy equation between points 1 and 2. So I have a pressure 1 gamma plus velocity 1 squared 2g plus elevation 1 is equal to pressure 2 gamma plus velocity 2 squared 2g plus elevation 2 and plus the head losses. In this case, we only have a local losses because the friction losses are equal to 0. So the local losses will be the sum of k's. So the sum of k's will be 0.03 plus the k of the valve. K of the valve times the velocity in the pipe. Okay, so that's what we are going to have. Okay, so the pressure in one and the pressure in two will be equal to 0 because they are atmospheric and they can cancel each other. The velocity in one will be equal to 0 because we have a reservoir. So we assume a large reservoir, therefore the velocity on the free surface will be 0 or close to 0. So this is close to 0. And then we have elevation 1 and elevation 2. If we use as a reference this line, at the center line of the pipe, the elevation of 1 will be 6 feet and the elevation of 2 will be equal to 0. So if we do that, the elevation of 1 will be equal to 6 and the elevation of 2 will be equal to 0. Okay, so we have a zeta 1 minus zeta 2, that's going to be 6. That will be equal to velocity in 2 squared divided by 2 times gravity, plus we have a 0.03 plus k valve times the velocity squared to g. So velocity is the velocity in the pipe, and velocity in 2 will be equal to the velocity of the pipe because there is no contraction at the outlet. So the velocity in 2 will be the same as the velocity in the pipe because of continuity. The flow in is equal to the flow out. So the pipe is not changing in diameter. So therefore, V2 will be equal to V, and V is the velocity in the pipe. So we have here then 6 is equal to, since they are the same, We can factor this, and then I'm going to have velocity squared divided by 2g. So I have here 1 plus 0.03 is going to be 1.03 plus k bulb. Okay. So what I am missing here is the velocity to be able to get k bulb. And the velocity is equal to the flow discharge divided by the area. We are given the flow discharge. In this case, the flow discharge is 0.12 cubic feet per second. So you have a 0.12 cubic feet per second. And the pipe diameter is 2 inches. So it will be pi diameter squared divided by 4. The diameter will be 2 divided by 12 to the square, all of this divided by 4. And this gives us a velocity of 5.5 feet per second. So now we can substitute for values in this equation, which we are going to call it equation 1. So we say in 1, I have a 6 is equal to 5.5 to the square divided by 2 times gravity, 32.2, 1.03 plus k bulb. The only unknown here is the k bulb. So from this, the k bulb we get is equal to 11.7, and that is the answer.